going to introduce Alan Stern. Alan Stern has deep ties to Tucson. I think a lot of you know him as the PI on the New Horizons mission that flew by Pluto a couple, gosh, is it 5 years ago now? 6 years ago. He's here representing Helicity Space, and Alan Stern, come on up.
Stephen, great conference, and thank you for the introduction. And that is a very bright light.
Yes, it's a very bright light.
All right, so I want to have a show of hands. How many people know about New Horizons? Ever heard about it before today? Right, first mission to the last planet. Right, how many people know that it was the fastest spacecraft ever launched? Right, it took 9.5 years to cross the solar system. To do that, we had to buy the biggest rocket that NASA would sell us, design the smallest spacecraft that we could imagine, and then top that biggest rocket, the most powerful version, by the way, of that biggest rocket, the Atlas V with 551, with a special purpose third stage. And the end result was such blinding speed that whereas Apollo missions took 3 days to get to the moon, we did it in 8 hours. That's 0.3 days. At that blinding speed that got us across the entirety of 3 billion miles to Pluto, it would take over 1 million years to reach Alpha Centauri. Clearly, we need better propulsion. And that's what I'm here to talk to you about. A startup company based in California named Helicity Space, which I'm privileged to be one of the advisors for. I'll tell you more about the company in just a couple of minutes, which has the explicit goal, it sounds like science fiction, but it's not, of developing a practical fusion drive in our time and to change the entire equation of how we do spaceflight, particularly around the solar system. So the talk's in 3 parts. First, I'm going to talk a little bit about the company. Then I'm going to talk about the Helicity Drive. And then I'm going to talk about an interstellar mission that we would like to fly, which does not go to another star, although its successors could. But it is, we think, a better way to skin the cat for the kind of, quote, near space interstellar missions that NASA is looking at. And I have to do all that in the next 12 or 13 minutes. Okay, so as I said, Helicity is developing a game-changing fusion drive, and it really is. People use that term game-changing a lot. This time we really mean it. Yeah, okay. So this is a very high-power device, and yet it's compact. Now, when I say compact, it's still tens of tons, but it's not the scale of the pyramids or a nuclear power plant. This is something that can be launched by existing launchers. It's clean because it's fusion. There's no radioactive fuels that are required. It's scalable in that we have, you will see, a variety of versions of this that can take us to very large payloads, even human class missions around the solar system. It's agile because it is continuously thrusting. You're able to abort a mission at any point. It's not like a ballistic trajectory like New Horizons, where once we got it going, there was no way to ever turn it around and bring it back. And it's reusable in the sense that the fusion drive allows us to send spacecraft out across the solar system, bring them in the drive back, fuel it up, and go do it again, and then do it again, and do it again. The same way that Falcon 9 rockets now fly again and again and again. Okay, so this is a cartoon drawing of sort of a cutaway of what this is about. It's been developed over a series of many years in terms of the requisite base technology, some laboratory demonstrations, a lot of modeling. You can see some of the organizations that are involved, ranging from Caltech to the Commercial Spaceflight Federation, the Fusion Energy Association, and others. And let me talk to you about the principals in the company. These 4 individuals, they're all here in the room today. Set Yu, Stefan Lintner, Marta Calvo, and Jeff Newman. And if they would stand up so you know who they are and you can ask questions later in the conference. They're the 4 of them from Helicity. That's the executive team. And then there's an advisory team as well, which I'm a part of. They're on the upper left. And another one of our advisors is in the room. Is Pete still over there? Pete Worden, General Pete Worden, former NASA Ames Center Director and Planetary scientist, in addition to a many other things in his career. So that's the company's advisory team. So we intend to fly the first fusion drive and to fly it as soon as we can. Okay, that'd be great. Let's do that. So, and we have a plan for developing this in 4 stages. Each stage is a 2 to 3 year development effort. We are at stage 1 and are currently raising the money for that stage, and very successfully, I should say. In fact, we're going to close our first investment round here just in a matter of weeks. And we're going to go from roughly a $5 million demonstration project, scale it by about an order of magnitude for the second stage, higher TRL demonstrations. Then we're going to take it to be an independent system, not plugged in a wall, not deriving power off the grid, but just like a spacecraft operating in a laboratory, still on the ground. That's about twice the price of step 2. And then with a demonstration mission out in space, flying into interplanetary space, which we think is about a $400 million enterprise. Add it all up, it's a little over $500 million, completely change the equation of how we do missions around the solar system, and change the course of the human expansion into the solar system in the 21st century. That's about a quarter the cost of a football stadium. It's amazing to think that we could change the course of spaceflight on just that. Next slide, please. Okay, so I've told you a little bit about the company. Let me tell you a little bit about Helicity Drive itself, the drive concept. And Set Yu, who can raise his hand from the executive team, is really the plasma physicist who is the brains behind this. He developed a lot of this when he was a professor at the University of Washington up in Seattle, and demonstrated it in a lab there before the company was formed. Next slide, please. So, in fact, the central picture right there, dead center in the upper middle, is in Set's lab, an actual Helicity Drive prototype firing successfully. And a variety of enabling discoveries have allowed this to become now a commercial concern. And the Helicity Drive is entirely based around a magnetic structure in a plasma that's basically a double helix, just like DNA, which combined with another technology that allows us to compress the plasma as the magnetic field is moving out through the plasma arc, gives us the ability to basically put an afterburner on an electric propulsion system and turn it into a fusion drive. Next slide. And here you see both in the on the right side, plasma actually moving through one of these devices, and then on the left with individual time steps, how this really works. And we intend to develop 3 different classes, possibly 4 classes of engines, small, medium, and large, just like your shirt sizes. But the way that these scale is not by making a bigger and bigger and bigger propulsion system. It's not like chemical propulsion, where we started off with relatively small engines and we ended up with, say, Saturn V F1 class engines. This is a little smarter approach. It's scaled by having more fusion guns. So you're adding engines. In the small version, only a half a dozen, or perhaps 16, and then going up into 21, and then going up into the 30s. And this allows us to get higher and higher fusion gains and higher thrust efficiencies until it eventually becomes self-sustaining, because the amount of energy it takes to sustain the engines driving the propulsion system is less than what the fusion is actually generating. Most of that energy going away to heat or to neutrons, for example. Next slide. Okay, so there have been a variety of physics-based experiments and numerical simulations that have taken place. And all across the bottom of that view graph, you can see a series of bullets, 5 or so in each of the 3 columns, of technologies that have already been demonstrated to prove this concept. I'm not going to read all 15 of them to you, but it's impressive what this company has been able to do on very small amounts of money to get this going. And it's so impressive that our first investment round is now looking to exceed its targets by a considerable amount, which we're pretty happy about because we'd like to do this as fast as possible. Next slide. So we have an ongoing integrated proof of concept demonstration that will be our step one. I actually want to start on the right where there's a scale model. You see the human in that CAD drawing next to the laboratory low TRL scale demonstrator. And then the 8 black boxes are the big batteries that discharge into the drive to power it for the tests that we will do. There are 4 milestones that we need to be able to demonstrate with this in order to go to the following step. And we think we can do all of this with the funding that we're now anticipating over the next 24 to 36 months. Next slide. Okay, so this is either an eye chart or maybe you can see it better than I can. But there's a lot of details here for all of you to be able to look at after the fact about these different drives as we progress from small, medium, large up to extra large, and then very, very much larger systems that will ultimately be powered not by deuterium, but by helium-3 when that becomes available. And what those allow us to do is to fly these interstellar missions, robotic precursors to what will, we hope, ultimately be human interstellar missions a century from now, with really impressive speeds that make New Horizons look like a horse and buggy by comparison. Next slide. Okay, so let's talk about plans for this interstellar mission. And next slide, please. Our proposed idea is to fly either a large or extra large class mission that can get us to distances like the Kuiper Belt, 30 to 100 astronomical units, not in a decade, but in 1 or 2 years. And if we fly the XL class system, that's not going to be first generation. We can do it in a matter of months. We can reach the heliosphere edge in about 3 years with the large class system. And ultimately, we can do that as well in months with the kind of systems that are on our drawing boards. And we can get all the way out to the inner Oort cloud, 1,000 astronomical units away. Remember, we're continuing to accelerate. So the speed's going up and up and up because it's a continuous drive. None of this, the current mode for flying around the solar system is you get a really big rocket, it develops all your speed. And unless you've got gravity assist, you're coasting from then on. But not in this system, like electric propulsion, but on steroids, we can get out to 1,000 AU in about the time that New Horizons got to 30 AU. And that is a game changer. Next slide. So let's compare it to other proposals to do interstellar robotic exploration of the very local interstellar medium. NASA is doing a spectacular study. The work is being led by the Johns Hopkins Applied Physics Lab, the same folks who built New Horizons. That's looking at a robotic spacecraft with very conventional New Horizons-like big launch vehicle, Jupiter gravity assist, maybe a solar gravity assist, an O-berth maneuver. And it's going to achieve speeds of about twice what New Horizons can do. A factor 2 is a big amount. But in the end, it'll get you out to the Kuiper Belt in 5 to 7 years. And it'll only allow you to have a fairly small spacecraft, like New Horizons, something the size of a baby grand piano to do it. Now, there's another mission that JPL is looking at called the Solar Gravitational Lens mission. And it uses a light sail for propulsion and a deep pass into the solar gravity well. It can get us all the way out to 600 AU, where the sun acts as a gravity lens so that we can look back past the sun at exoplanets opposite the sun on the far side and image them at unprecedented resolution, tens of kilometers, so that you could see the lights of New York City on the Earth at that resolution. But that mission still takes 25 years to get out to that gravitational lens. By comparison, a Helicity-powered mission could fly out in a much shorter period of time and carry a 5-ton payload. So we can do these amazing things that we could never otherwise do. We could carry a Hubble Space Telescope class aperture out there and really do astrophysics. With orders of magnitude more power that's available to run the instruments and to communicate all that data back to Earth, and many other advantages. So we think this is kind of a no-brainer, other than the fact that we have to develop and prove this technology that we talked about. 5 minutes. Okay, so if we can have the next slide, and I'm almost finished. Scientific objectives for a mission like this are really mouthwatering. And the JPL and APL studies have borne out the same thing that we have said. This is a great mission for planetary science, particularly the Kuiper Belt. It is a great mission for heliophysics. That's another division in NASA's Science Mission Directorate for studying not just the interstellar medium, but also the termination shock and the heliopause, the shape of the heliosphere, the energetic neutral atom ribbon that was discovered by the IBEX mission, all of that in one mission with all the instrument goodies that you want, because this is not mass starved. And it's great for astrophysics, exoplanet studies, the things that you will do at the solar gravitational lens. So this is the kind of flagship mission that we hope will come out of the heliophysics decadal survey. Next slide. And we can fly it with either of two architectures. One would be the L class or large class drives that will be available by demonstration about a decade from now, according to our business plan. And those could fly on a Falcon Heavy. The system is big, but it's got plenty of margin, plenty of mass margin to be lofted by an existing launch vehicle, the Falcon Heavy. And that system can fly the 5 tons of spacecraft and payload that we were talking about, along with the propulsion system that weighs about 34 tons. The XL, which is the really fast ship, that's a little bit further down the road, is much heavier, but not so heavy that it can't be launched. In fact, the NASA Space Launch System is big enough to launch this vehicle. Imagine that, launch something that can take us all the way to the stars, that could take us to Alpha Centauri in about a century. That's a tractable length for a robotic spacecraft. Voyager, intended to go only to Jupiter, Saturn, is now nearing its 50th anniversary in flight. They weren't even trying to do it. With these propulsion systems that Helicity is developing and existing launch vehicles, we can do interstellar missions robotically, launched in the 21st century, arriving in the 22nd century, and that's not science fiction. Next slide. So this brings me to the conclusion of our talk. We're all about going faster and farther. And I hope that with this talk, I've given you just a taste of what Helicity Space is up to, and what our ambitions are, and the very bright future that we see for interplanetary and interstellar travel with the Helicity Drive. Thank you.
Thank you, Alan. So our first question, if you can make fusion work, why not do that first in the lab for commercial power generation?
Yeah,
the billions you'd make as a provider of carbon-free energy, you could then fund interplanetary/interstellar travel on the side.
Except, and this was actually one of the first questions I asked when Helicity, the company, approached me to join as an advisor, is, I've been watching fusion power development on the ground for ground-based power production purposes, and it's been impressive in some regards, but it's always another 20 years off, and it's been that way for 50 years. And as Seth very well explained to me, this is much easier than doing a fusion power plant. This is really just an afterburner on an electric propulsion system that uses fusion technologies to achieve that high thrust and therefore that acceleration without many of the complexities that you would have if you had to try to have a sustained tokamak or other ground-based fusion power system. What's the second question?
Thank you. Actually, I'm going to combine a few here. Could you tell us about the fuel or the pulsed power source?
Well, the fuel for this system is initially going to be deuterium-based, but we hope to go to helium-3 for a number of reasons. But first, we have to have sufficient helium-3 supplies to be able to make that happen. As to the pulse power, I'm going to actually ask if Seth can stand up and speak to that himself. You'll have to project a little bit. We got a mic for you.
It's a pulsed magneto-inertial fusion concept. So on the ground, it's going to be energy stored, electrical energy stored in capacitor banks that would be discharged into very high currents inside the plasma. And then you time it with the magnetic fields, external magnetic fields, to be able to compress the plasma to fusion conditions in a very short pulse.
Thank you. And I believe we're out of time, but the final question I'll try to answer myself. How can we invest in Helicity Space? Please talk to one of the 4 co-founders over there, presumably.
Stephane, Stephane's our company CEO. Go see Stephane. He's got a term sheet and he's finishing the round. There may be a chance for you to still get in.
That's perfect. Thank you,
All right.
Alan.
Thank you very much.
Thanks very much.